This is a satellite foundational course for GOES-R on fog formation and dissipation with a focus on how to detect fog. I'm Scott Lindstrom from SIMS, and I will lead you through this training. Learning objectives are on the left. You'll learn which GOES-R ABI channels and products can be used to detect fog's presence and to monitor its evolution. Note the acronyms you'll see in this training, boxed in yellow at the bottom. Subject matter experts for this training are listed on the right. Mike Pavlonis from NOAA and Corey Calvert from the Cooperative Institute for Meteorological Satellite Studies. Brightness temperature difference detection of clouds made up of water droplets works because water droplets in clouds are not blackbody emitters of 3.9 micrometer radiation. The conversion of satellite detected radiance to temperature assumes that an emitter is a blackbody. For the case of 3.9 micrometer radiation above cloud droplets then, where the amount of radiation detected will be less than that emitted as a blackbody, the inferred temperature is too cold. Clouds do emit 10.3 or 10.7 micrometer radiation, more like blackbodies, so the inferred brightness temperature won't be so cold. In this cross-section from a fog bank to a cirrus deck, you see brightness temperature differences over the fog that are related to emissivity differences in the cloud, so that the 3.9 micrometer brightness temperature is cooler than that at 10.7 micrometers. Over the cirrus, subpixel effects cause a difference so that the 3.9 micrometer brightness temperatures are warmer than the 10.7 micrometer brightness temperatures. In clear regions at night, the 10.7 and 3.9 micrometer brightness temperatures are similar. This shows Himawari data over northeast China near the Korean peninsula. Himawari and GOES-R have similar bands. Himawari band 13 at 10.4 micrometers, shown here, shows a fairly flat field. The AWOPS probe shows temperatures from 10.4 and 3.9 micrometers at a point. Note that the 3.9 micrometer brightness temperature is much cooler in many places, not just at the probe, as is obvious based on the 3.9 micrometer imagery you're seeing. Stratus clouds are filling the valleys in this region of Asia, and emissivity differences from the water droplets in the cloud drive temperature differences between the 3.9 micrometer channel and the 10.4 micrometer channel. Those differences highlight low clouds, fog, and stratus. The difference field between those two infrared channels shows signatures similar to this visible image from shortly after sunrise that confirms the presence of clouds in the valleys. But do those clouds extend to the ground? That's a hard thing to determine from satellite data. Low stratus is indicated in these images by the brightness temperature difference field, the regions enhanced in blue, meaning positive values at night, in the lower left. You can also infer the presence of clouds because you can't see surface features like rivers in the single band imagery. The advanced nighttime microphysics imagery also indicates stratus, with the blue or cyanish hue in the same region as the brightness temperature difference field. Here's the question. Is this stratus or fog? Is there stratus under the high clouds over Georgia and Tennessee? How can you tell? GOES-R IFR probability fuses cloud information from satellites with model information, the rapid refreshes used over CONUS, about low-level saturation. Other static information is used as well to create a statistically generated prediction about the probability of IFR conditions. Saturation information from the model screens out regions of mid-level stratus that are usually unimportant as a transportation hazard. Saturation information from the model also reveals important information about low clouds under cirrus. Model fields can struggle to depict small-scale fog events like valley fogs that occur at subgrid scale resolutions that satellites can view. The fusion process takes the strengths of both systems, satellite and model, and allows for confident identification of MVFR, IFR, or low IFR conditions even when one of the individual predictors fails at highlighting their potential. IFR conditions were selected for this product because it has a well-defined limit, unlike the more nebulous word fog. So here's the view over the Carolinas again, but IFR probability has replaced the RGB. Because information from both satellite and model are considered, IFR probability can give a consistent signal in regions where cirrus clouds block the satellite view of low clouds, such as over northeast Georgia. Model fields there suggest low-level saturation, so IFR probability is enhanced. Stratus and fog can look very similar from the satellite, but saturation information from the rapid refresh allows IFR probability to screen out regions of mid-level stratus, such as over central South Carolina, where the rapid refresh is not suggesting that low-level saturation is occurring. The previous slide showed IFR probability, but there are actually three probability fields for MVFR, IFR, and low IFR conditions as shown here over New England. As you might expect, MVFR probabilities are always greater than IFR probabilities, which are always greater than low IFR probabilities. Cloud thickness is a GOES-R product that estimates the vertical thickness, cloud base to cloud top, of the lowest water-based cloud layer. This product is essentially a lookup table that compares 3.9 micrometer emissivity to SODAR observations of cloud thickness off the west coast of the United States. GOES-R cloud thickness is not created in regions of multiple cloud layers because satellite information on the lowest layer is missing in such cases. GOES-R cloud thickness is also not computed during twilight conditions because of rapid changes in the reflected component of the 3.9 micrometer radiation. The fields shown here have two distinct regions. Over coastal Maine, the satellite has an unobstructed view of low clouds. Probability fields are pixelated, reflecting the variability inherent in satellite data, and GOES-R cloud thickness can be computed. High clouds are present over eastern Massachusetts, and probability fields there rely on model data, and they consequently look much smoother because of the smoothing that occurs in the model and because of the relatively coarse model resolution. When river-valley dimensions are smaller than the model resolution, as is often the case with small rivers in, for example, Appalachia or the Ozarks, or in this case over Wisconsin and Iowa, satellite information will accentuate river valleys in IFR probability fields. In fact, you'll often see an IFR probability signal there first. GO16 and GO17 have 2 kilometer resolution at the subsatellite point. Rapid refresh horizontal resolution is 13 kilometers. These images show topography constraining low clouds around the Snake River in Idaho. Occasional cirrus here makes the brightness temperature difference field suboptimal for fog detection, but IFR probability fields maintain a consistent signal. GOES-R cloud thickness, the last one before sunrise shown here on the y-axis, and fog dissipation time on the x-axis are related. The points on this graph were determined by hand for radiation fog only, mostly for cases over the southeast United States. If the last cloud thickness value before sunrise was at 11:45 UTC, and it showed a cloud thickness of 900 feet, the best fit blue line suggests a dissipation time of about 2 hours later, at 13:45 UTC. This example demonstrates the utility of cloud thickness in predicting dissipation time. The still figure is cloud thickness, the last one before morning twilight conditions, and in fact you can see the data cutoff right off Florida's east coast. Values are very small. Magenta is around 300 feet, blue is closer to 400 feet. Those small values suggest rapid burn-off, and that's what happened as shown in this animation. Note that the region with the thickest fog did have fog for the longest time, but that almost all is gone by 13:07 UTC, 2 hours after the cloud thickness image. The model data used in IFR probability varies by region. Domains and resolutions are noted on this slide. If you're forecasting outside of North America, you might see probability differences at the model boundaries because GFS and rapid refresh solutions will vary. There are occasional stray light issues around the equinoxes and brightness temperature difference fields, and that can affect IFR probability fields. That's not shown here, but be aware of it. This slide shows the discontinuity in IFR probabilities during the transition from day to night and vice versa. Satellite predictors used during the day differ from those used at night. In general, IFR probability increases during the day because of changes in the statistical predictors used. The GOES-R cloud thickness product, again, is not computed during twilight conditions, but it is available all night and during most of the day for single-layer water clouds. GOES-R has routine 5-minute data over CONUS. This is handy when precise information on dissipation time is required. If you need even more precision, request a meso and get 1-minute data. GOES-R IFR probability is statistically superior to brightness temperature difference fields in predicting IFR conditions. You've already seen cases that should convince you of this. If high clouds block the view, IFR probability can give a good signal based on model data. If stratus is elevated, IFR probability will screen out the region based on model data. Both of these examples will lead to better statistics for GOES-R IFR probabilities. The validation here was performed using 1 day from each month, and there are roughly 1100 goes east scenes. The CSI for IFR probability is roughly twice that of brightness temperature difference fields for lower IFR probability values. Brightness temperature difference fields are challenged to provide information about cloud ceilings, as the satellite sees only the top of the cloud. Brightness temperature difference fields cannot give information when high cirrus obstructs the view of low clouds. IFR probability fields in these cases can augment the satellite to give a more complete description of the near-surface saturation. GOES-R cloud thickness fields can be used to predict fog dissipation time. This concludes the Satellite Foundation course for GOES-R on fog detection and dissipation. Thanks for listening.